Let's get back to the video here. Today we're going to talk about what does a signal or signals look like as it goes through an IQ demodulator. And we're going to keep doing these series until you're sick of IQ data and you know it inside and out. It's still a rather confusing topic for most people, so today we're going to try our best to make it real simple so that you understand what the hell's going on. Alright. So let's say we got two signals, signal A and signal B. Signal A is at 21 megahertz there, and signal B is at 18 megahertz. Now, these could be AM, FM signals, some digital signal, we don't care. So we're just simply showing you two signals here, signal A and signal B. And we got a 10 megahertz span centered around 20 megahertz. All right. Hopefully that's real simple. Alright, so our question today is, now we have this IQ demodulator, and if we set the internal LO of the IQ demodulator to 20 megahertz, and we go through these two low-pass filters with 5 megahertz cutoff frequency, what do these two signals at 21 meg and 18 meg look like as they go through the IQ demodulator? So that's kind of what our question is. And hopefully you will see, because we got 5 and 5 there, the IQ bandwidth is 10 megahertz, not 5. That's always a tricky one that confuses people. But again, because you got an I signal and a Q signal, both with 5 plus 5, last time I checked was 10, so the IQ bandwidth is 10 megahertz, not 5 megahertz. Alright, so hopefully the smart ones of you figured it out. The signal that leaves the IQ demodulator is now a complex signal. We'll call that Z. It has a real part and an imaginary part. Now, we just made it that way to keep the math simple, but that's what it is. So, the signal that was at 21 megahertz now is centered at 1 megahertz, and the signal that was centered at 18 megahertz is now centered at negative 2 megahertz. So, that's what we mean by negative frequency. It just says it's 2 megahertz below 20 megs, because 20 megs is what we arbitrarily set our LO to in the IQ demodulator. So this is the spectrum here that shows what it looks like in the complex domain after an IQ demodulation with the LO set to 20 megs. Signal A is now centered at 1 megahertz instead of 21. And signal B is now centered at negative 2 megahertz instead of 18 megahertz. And that's simply because it's now, the two signals are now related to whatever the LO was, right? And in this example, we set the LO to 20 megs. So, hopefully everyone's getting that. If not, you can draw it all out mathematically, and after 40 hours, you realize I was right. So, but if you just want to get to the proof of the pudding, well, then just trust me. Alright, so we got these two signals at 1 megahertz and the other signal at negative 2. So that is their spectrum. How do we represent this signals in time? And we call that Z of t. And the equation there at the bottom here is kind of showing that. You got e to the j, 2 pi, 1 megahertz times signal A in time, plus e to the negative j for negative, 2 pi, 2 megahertz times time, and that's times signal B in time domain. So that's how you represent those two signals now. Now they are complex signals simply because they are after an IQ modulator. And they're simply complex because we simply just made the Q signal be a complex signal. They weren't naturally complex. Don't ever think about it. We're just making the Q signal be complex, and then that allows us to use all the complex mathematics that a bunch of mathematical nerds wrote 200 years ago and didn't have any application. Notable people like Euler and things like that. They had no idea about the modern digital communication revolution. They were just writing these mathematics back in the 1800s simply because they were bored and had nothing better to do. But anyway, thanks to their hard work, we can now use these equations for complex signals and digital signals in our modern world. So I hope that kind of explained today what two signals look like after they go through a IQ demodulator.